We're finally moving on to the largest objects in the universe: galaxies, galactic clusters, and superclusters. Here are the learning outcomes for Unit 4B. Go ahead and pause the video and write these down. So I have a question to begin with. Is it possible with the right technological advances that we could someday travel to the nearest star? And I don't mean the sun. A lot of people wonder this. So I wanted to give you some actual numbers. Here's a little cartoon between Earth and Pluto, which is about a 3 billion mile distance. Conventional ion-driven spacecraft travel at a speed of about 27,000 miles per hour. Maybe someday this will even become a faster number, but we'll never be able to travel even remotely close to the speed of light because that's physically impossible. So let's take a look. How long would it take to travel to Pluto? Well, we've actually sent spacecraft out to Pluto, and we know it takes about 10 years. So would you like to go visit Pluto? Get on a spacecraft, hang out for 10 years, check it out, come back? Probably take you a total of 25 years out of your life. Well, maybe it's worth it, maybe not. I'm not sure. But what about the nearest star? So the nearest star is called Proxima Centauri, and it's 25 trillion miles away, or 4.2 light years. That means it takes light 4.2 years to travel between our solar system and Proxima Centauri. So if we got on a spacecraft to travel all the way from Earth, it would take 70,000 years one way. Just think about that for a moment. Can you imagine getting on a spacecraft and thinking, well, I'm going to be the beginning generation. Here we go off on a journey where we're going to have at least 100,000 generations living on a spacecraft to get all the way to the nearest star. And then imagine you hang out there for a couple hundred generations and then decide to send a ship back to Earth. Takes another 70,000 years. We wouldn't even be the same species anymore as those who went off in the spacecraft. It's really not possible to travel even to the nearest star. We're trapped in our solar system by physics. Let's talk about the nearest large galaxy, the Andromeda galaxy. That's 2.3 million light years away. It takes light 2.3 million years to travel between the Andromeda galaxy and us. There is just no way we're going to visit any other galaxy. It's just not possible. Okay, moving on to our topic of galaxies. There are three general types of galaxies: elliptical, and here's an example, spiral, an example, and irregular, and another example. Now I know in your homework, when you watched the video about galaxies, the narrator mentioned 4 types of galaxies: irregular as well as peculiar. His definition for peculiar meant that they were galaxies that had a strange shape and were probably the result of collisions. And then his definition of irregular were galaxies that were chaotically shaped. We're going to just group those together. All right, let's look at each type. So spiral galaxies have arms extending from the center. About 20% of all galaxies are spiral. They're very large in size, and they contain young and old stars. Our Milky Way galaxy is an example of a spiral galaxy. There's a special subcategory of spiral galaxy called barred spiral galaxies, and these seem to have a bar in the middle of stars, just like shown here in the right. These are generally quite large, and about 10% of all galaxies seem to be barred spiral galaxies. Here's a spiral galaxy. Here's the same barred spiral galaxy taken with 2 different kinds of photography. Here's a spiral galaxy in the constellation Andromeda. Here's one of my favorites, the Sombrero galaxy. And here are some other pictures. Now I wanted to point out on this one, where we have an edge-on view, that there are these things around it called globular clusters. And these are clusters of thousands of stars that seem to be gravitationally held to spiral galaxies. We have some in our own Milky Way as well. So let's talk about the Milky Way. Our galaxy is a spiral galaxy, and we figured out by using radio telescopes in all directions to try to understand its structure. Remember, we can't even travel to the nearest star, so we certainly can't travel far away from our galaxy and look back at it. Our galaxy is about 100,000 light years wide and about 10,000 light years thick. there seem to be three major spiral arms of stars, and the sun is about 30,000 light years from the center of our galaxy. So here's a cartoon. Again, we can't go out and look back at our galaxy. Here's the sun. Remember, we can't even go there to Proxima Centauri. The size is 100,000 light years across, and this is what our galaxy might look like if we could see it from a distance. This is what the edge-on view of it might look like. A lot of mass is concentrated in the center, where we believe there are lots of black holes as well. Now you can see those globular clusters in this view. Here's an actual image of a globular cluster with thousands of stars. These stars tend to be very close together compared to stars in our galaxy. And if you look, you can see lots and lots of red stars in here. So there are lots of red giants in that particular cluster. How does our galaxy move? Well, we rotate like a pinwheel around the nucleus. The outermost stars actually move slower than the innermost stars, which is an interesting parallel to the planets going around the sun, right? The farther the planet is from the sun, the slower it goes. The sun goes around the entire galaxy about once every 200 million years. So we've made an entire rotation since the time that the dinosaurs dominated the Earth. There's this galactic halo that's sort of a spherical region around our galaxy that contains gases that are very loosely held, and this is where the globular clusters are located. Here's a view from Earth of our Milky Way galaxy. We're looking towards the center, so this is where that central bulge is in the galaxy, where we have a lot of the mass and probably a lot of black holes. The dark stuff that you see in the way is nebula that's blocking light. And here's another view from Earth. There is the Milky Way edge-on. Another type of galaxy after spiral are elliptical. These have no arms, and about 60% of all the galaxies we observe are elliptical. They seem to contain old red stars, and they're believed to form from the collision of two spiral galaxies, which was also described in the galaxy video that you saw for your homework. Here's two pictures of some elliptical galaxies. Here's another few. This one here is a spiral galaxy, but then there are two elliptical galaxies nearby. Finally, there are the irregular galaxies. These lack any kind of symmetry, and about 10% of all galaxies we see are irregular. They mostly contain young stars, and an example is the Magellanic Clouds. Here's a picture from Earth of the Milky Way and small and large Magellanic Clouds. These are named after the explorer Magellan, who was one of the first to notice these objects. These are only visible from the southern hemisphere. So we've talked about the three kinds of galaxies. What's bigger than a galaxy? A galactic cluster. So a galactic cluster is a gravitationally bound group of galaxies. Some of them contain thousands of galaxies. We're part of a galactic cluster called the local group, and we have about 40 galaxies in our cluster. This is a cluster that's about 1 million light years from Earth, showing a number of galaxies. Here's another cluster called the Fornax cluster, and here's a cluster called the Abell 2218 cluster. So in some cases, clusters can have thousands of galaxies. Here's an image showing our local group. The top part here shows the Milky Way in the middle and a radius of almost 1 million light years, showing where members of our local group are positioned. And we have a key down here: yellow are spiral, blue are elliptical, and red are irregular. If you take this entire region and you put it back in the middle, down here we have a 5.5 million light year radius. And so you can see the Andromeda galaxy is here, as well as numerous other galaxies. What's bigger than a cluster? Well, a supercluster. These are huge swarms of galactic clusters, and they might be the largest entities in the universe. We're part of something called the VIRGO supercluster. So here we have another kind of image showing 100 million light year radius. The local group is just positioned in the middle. And then these are other clusters. The Fornax cluster I showed you a picture of. These are other clusters. And you're starting to see, if you look at the white dots here, there is a pattern here where there's dense clusters of galaxies and then big open empty voids. After this video, there's a short video called the LANIAKEA supercluster. It's about 4 minutes long, and it's a great little video. It describes the LANIAKEA supercluster and places our VIRGO supercluster within it. Here are neighboring superclusters. So we've got the VIRGO in the middle, the Centaurus supercluster, the Sculptor supercluster, and now you really can see that there are areas with lots and lots of empty space, and they're called voids. Here's the Buddhist void, the Capricornus void, the Sculptor void. There seems to be a fabric to the universe. Mass is not uniformly distributed. What if we look in all directions? Well, here we are looking about 14 billion light years in all directions with us in the middle. And you can see that there's again a pattern that almost resembles the granules of the sun, where mass is concentrated in some strands and mass is missing in others. Coming up next, the fate of the universe.